Don't make it too hard.
Like 2. Basically 2.
Okay, or 6. I don't know. I heard 6 up there, so we went with 6. Bless you. Example of an exponential function is this. You did this in chapter 7. So now what was the inverse of that function look like? So what does inverse mean? We talked about it yesterday. We flipped the x and y values. So this is going to be x equals 6 to the exponent y. Right? This is what yesterday in our exam review stuff. Switching the x and y values. All right. So now what we're going to do, so before we, in chapter 7, 7.3, we made them like bases and then we solved. But here's the thing. X can't be a like base to 6. It's not going to work out. There's no way of all of our skills we have so far that we can solve that. So this is where logarithms comes in. So the whole point of logarithms is being able to solve for situations that we can't get to like bases. We're going to get pretty exact. Okay, so if I have it in exponential form, x equals 6, y. So let's break through those. So this is my base, and that's my exponent. Okay, you with me so far here? So if I was to put this equation into logarithmic form, this is what we're going to do. The exponent moves out into the front. We're going to write log. And it's going to be base 6. That's the base. That's the exponent. And it has to be a log of something. So it's the log of what it was equal to. We call that the argument. Here again. Oh, look at this. Today my technology is working. So logarithm is the word that we're filling in here. I'll put a TH in it. So what we're doing is we're taking that exponent and we're putting it in a place we can actually solve for it. So we have to use logarithms to do that. All right. So easy peasy. We did this a million times yesterday. David, what's my table of values? Come on. For this equation, we did this how long ago? A year ago? Okay. You're just the king of tables. No? When are you going to entertain it? Matthew's back. We'll be back now. Great, we did that in chapter 7. That's good. You guys can do that easy peasy. So now we're going to do it. We're going to do it the inverse of that. So what happens to my table of values? They get switched. So my x is a quarter, now my y is -2. My x is a half, my y is -1. This is 1, this is 0. So now when I graph this, hey, what's my problem? What didn't I do here? We talked about getting my table of stuff. Increments. I did. So at a quarter, I'm at -2. At a half, I'm at -1. At 1, I'm at 0. At 2, I'm at 1. At 4, I'm at 2. Try not to lose any marks this time. Do I need to label 2 points if I have a table of values? So what do you notice about these? First of all, let's talk about the asymptote. What do you notice changed about the asymptote? It was horizontal, now it's vertical. Okay? We have an increasing function. Is this increasing? As the x's are getting bigger, what's happening to the y's? They're getting bigger. So it's also an increasing function. They just look completely different because of the asymptotic behavior. Hey, would you guys strike any marks for this? Do you feel that that's moving away from the asymptote? Close enough, we're good. Would you? Nice. Okay. I think this one's better. It approaches the asymptote, doesn't seem to curl away. I look at this and I think like my leg's starting to curl up. So just keep that in mind as you're going through. Pretty easy stuff, right? So this, what's the inverse to that? What's the inverse to this equation? X equals 2 to the power of y. So write that as a logarithm. Write that as a logarithm. Y equals log base 2 x. So I'm going to be asking you to switch forms with them back and forth. So now if we looked at this, could you put that in exponential form for me? Go. You did the last unit. You were good for the last unit. You didn't watch the video? I want to rush it all the time. Leave it on the last minute. Did you look at your project out? You know what? I don't. Okay, perfect. So if I were to put this into exponential form, it's going to be base of 3 exponent equals x. So what is that? That's the inverse to y equals 3x. This I don't want to graph. I want to graph this. But knowing this table of values is going to be helpful. Or doing a table of values for this one. Let's not do 2 tables of values. So in this case, what am I going to pick? I'm going to pick my x values like I normally do, or I'm going to pick my y values. I'm going to pick my y values. Remember, they're just switching them, right? Like here, we would pick our x values. We're doing the inverse of it, so we're going to pick our y values. So this would be the -2, -1, 0, 1, 2. That doesn't make sense, or that? Okay. So now knowing that, if y is -2, we know x is 1/9, 1/3, 1, 3, and 9. Because I want you to put 2 into this equation. So 3 to the exponent 2 is 9. So when you get a logarithm, pick y values. Does that make sense to everybody? I don't know if that's a good way, or do the table of values for this and then flip them. All right. So let's graph this. Where do you anticipate in a logarithmic graph your asymptote to be? It's going to be vertical, because in an exponential graph, it's horizontal. So in a logarithm graph, it's going to be vertical. So if you cross the y-axis and there's no transformations, you have a problem. So we'll go 5, -5. Look at me, not losing marks. -1/9 is really, really close. So that's going to be -2, or positive 1/3 is going to be -1. At 1, I'm at 0. At 3, 1, 2, 3, I'm at 1, and I'm not going to get that other point. What's the common point on the logarithm graph? 1, 0. What's the common point on an exponential graph? 0, 1. They just flip, right? Okay, so let's do the logarithm graph for this one. Something else actually works, which is weird. All right, so put this in exponential form. So I'm going to have a base of 1/2. Remember that that has to be in brackets. I'm going to apply an exponent of y, and that's going to be equal to x. So if I'm doing a logarithm graph, what am I picking, x's or y's? Y's. So -2, -1, 0, 1, 2. -2 is 4. 2, 1, 1/2, 1, 4. Sometimes I find it easier to do the down part of the chart, like to do an exponent of 0, an exponent of 1, an exponent of 2, and then the negatives kind of come more naturally. Okay, so at -5, not losing points anymore. So at 4, I'm at -2. At 2, I'm at -1. At 1, I'm at 0. At 1/2, I'm at +1, and at 1/4, 4. What kind of function is this? Increasing or decreasing? Decreasing. As the x values are getting bigger, my y values are getting smaller. So it's a decreasing function. That's pretty exciting. Okay, so we need a range of a logarithmic graph. What's the domain? What's the range? Okay, I'm not going to ask you to pull out your notes, but if you were to look at the characteristic list of exponential functions, these are flipped. What does that mean, Kevin? What does it mean? What does it mean? What does it Really? Okay, please remind me to come back to it because I know what it is. Okay. I think so. If not, we could Google it, right? All those sales. Except our internet's been crappy. So, okay, what's the common point? We talked about that. 1, 0. So the x-intercept would be at 1. What don't we have? There's not a y. What don't we have? Y-intercept. Don't you love fill in the blanks? Like you have no clue. Like there's not a lot of clues in that statement. Yeah. Okay, wait a minute. Yes, the function and its inverse are both labeled as functions. Like the original one and its function. Okay, so let's go back and fill that in so you know what that means. So Matthew said it passes the horizontal and vertical line test. And for us mere mortals who can't remember what that means, it just means that the original graph and its inverse are what? Good job. Did you Google that or did you pull that as a whole?
I can Google it.
Okay. Did you Google stole it from Matthew. Awesome. Okay, so if we have no y-intercept, what do we know about the vertical asymptote? X equals 0. All right, so going back up, we're looking at these two graphs. As if we have a base of a function that's greater than 1, we know that this graph is an increasing function. If the base is a fraction, then okay, so you need to know all this stuff about your graphs. So, oh, Matthew, you're doing chapter 8.
Yeah.
You know what you're doing? No, I mean, you don't know what we're doing. Did they tell you? We're all making exam cheat sheets for a chapter. Your last time standing, so you got chapter 8.
I don't like this. I want to read it more.
It's all right. Jerome. Everybody wants it. It is. It's Can you handle that? I have a format for you to follow. But what you're doing is everybody's going to do a chapter. Everybody's going to do a chapter and then like compile them and give you a whole set. So really, you're only doing 1, you're getting 11. So if you don't do your 8, you let all of these people down. Peer pressure. How do you let down that?
I was joking.
Okay. All right. So I've given it to you in logarithm form. I want you to put it in exponential form. Easy. Okay, Carson, I'm going to ask you. What's the base? I'll come out, David. Nobody has notes back then.
Yeah.
The base is 5. So if it's the base on the logarithm, it's the base on the exponent. The base is still the base. No. So if it's a base on the log, it's going to be a base on the power. That's nice and easy to remember. If it's a base, it will stay a base. Where's your exponent? Your exponent is, no, your exponent is the outside one. So, and that's equal to the argument. Because the whole point of doing logarithms is being able to solve for an exponent, right? So this out here is your exponent. It's handy if you can go back and forth between. Okay, so I put this little remember thing. You guys have to be pretty careful with how you write things. Some of you tend to be a little bit sloppy. If you did this, no problem. That is a log base 10. Because we're going to learn that logs don't always have to show their base. If there's no base stated, it's automatically assumed that it's 10. I'm looking to you guys. But if you write something like this, you're going to get a conceptual error because you don't know where the base went. Okay? So don't be sloppy in your writing. Make sure that base is a subscript. Okay, so if I was to put this into exponential form, what would it look like? What? X is equal to a to the power of y. So these two things are equal. They mean the same thing. It's not the inverse, it's like taking a fraction of a half and calling it 2/4. It's just another form, but they have the same value. Okay? These aren't inverse to each other, these are the same thing. All right. Let's solve these in exponential form. So what am I going to do? Do that. So what's it going to be? Base 9 to the power of y equals 27. So this is your chapter 7 knowledge coming in. So what am I going to do? 3's. So 3 squared y equals 3 to the exponent 3. So what's y equal to? That makes sense to everybody?
Yeah.
We'll get more complicated really quick, so don't worry about it. So we've got base b to the exponent 3/4 equals 8. People really struggle with this one.
Wait, this will be trying to think of.
Okay. All right, you do you. What do you mean you're good? You figured it out?
No, I'm just trying to figure out, what this is default.
These are tougher. Okay, so the whole point is I want a single b, right? I want b to the exponent what? 1. That's my goal. So what do I have to do to the exponent here to get rid of some stuff? So if I was to write this as a radical, this would be the 4th root times b cubed equals 8. Sometimes it's easier to see if you were to do that. So how do I get rid of a 4th root? I'm not cubing it, I'm fourthing it. You like that? Okay. The exponent of 4. Sounds better than root. So now I've got c cubed equals 8 to the exponent 4. How do I get rid of the cube exponent? You root it. So now I got b equals the cube root of 8 to the exponent 4. This isn't hard. No, we're going to do it without a calculator. No, don't do that. It doesn't matter what order you do them in, whether you do roots or exponents. So what would I do first? I cube root it, because what's the cube root of 8? So it's 2 to the exponent 4. Okay, can I tell you a faster way to do it? He's like, no, don't do that. I showed you all the steps. I showed you putting it into a radical and things like that. You need to get this to an exponent of 1. So another way of doing that would be to multiply by the reciprocal. Right? Because this will cancel out this, and the 3's will cancel out, leaving you with just 1 on top of the b. Right? But if you multiply this exponent by 4/3, you have to multiply this exponent by 4/3. And we did do a cube root. And we did do an exponent of 4. We did it all. I just showed you all those steps. But you can skip showing me all those steps and just multiply by the reciprocal to get it to 1. Gotta learn the basics, man. We're not there yet. We're not there. We're not there. Okay, so the first thing I want you to do is I want you to do a side note. They were important in completing the square, and they're just as important now. So I want you to do that inner log as a side note. So I'm going to go log base 3 9 equals some variable. I don't care what the variable is, I'm going to call it k. What? It is 2. But some of us haven't taken the
I
This is what I say to you every day. I feel like this is a conversation I have on a regular basis. We have to practice. It is 2. If you know it's 2, just put 2 in there. I have no problem with that. But if mere mortals are just going to try to work through it, this is the first time we've ever worked with logs. Can you imagine if I walked in every day and said, we've done this, you should just know it is 2. It's not really great of a teaching style. Are we done? Thanks. King. Put in an exponential. Put in an exponential part. Thanks. So you can see that it's 2, but I'm going to show you all the steps because that's the kind of nice person I am. Okay, so what you know now is that this has a value of what? 2. So now we're just going to write it as log base 2 I'm going home. It's true, it's true. Okay, put it in exponential form. 2 to the power of x equals 2. So that's a 1 over there. So x equals 1. Hey, no, wait. I don't want to move. Okay, another kind of quick thing. Okay, so if you get into a situation like this is a known truth in mathematics. Just like your Pythagorean identity, like sine squared theta plus cos squared theta equals 1. You don't have to prove it to me. So if you see this, you know automatically that if the base and the argument are the exact same thing, base and argument are the exact same thing, the value of that logarithm on this side evaluates to 1. Makes sense to everybody? So that's a known truth. You don't have to prove it. You don't have to show me all the steps. You just know that that's true. It's a known truth. And if you want to prove it to me, have at it. You don't have to. Okay, logs that have a base 10, you smarty pants McGee's. Logs that have a base 10, what do we call those? What do we call them? They're not just logs. They're common logs. I'm so glad I got to teach you guys. It's hard being your teacher when you already know everything. Okay, so let's evaluated with the calculator, base 10. You cannot solve base 2 logs in your calculator. The only, when you see that log button in your calculator, it's a base 10 log. I know there's a way to do it. I know how to do this, but
It's helpful.
it is super helpful. But we're not there yet, Kevin. We're not there yet.
I don't think I know that. That is not.
Can I as well? Is that possible? We'll just drop this class?
I'll take over.
Perfect.
I'll
Thank
drop it
God.
off and keep the hard drive.
Yeah. Okay, let's do it without a calculator. So that's going to be putting it in exponential form. So I'm going to set this equal to some variable. I'm picking k. So it's going to be 10 to the exponent k equals 100. Can you rate 100 as a base 10 number? Yes.
Reload this number.
Okay, so now get your calculator out. All right, so in your calculator, when your logarithm is a common loss, when it has a base 10, so this log button, where's my log button? This log button right under your x squared button, the one below it, that is a base 10 log. So it won't evaluate properly if you put in, if you're trying to do base 2, but we can do base 10. So all you have to do is hit the log button and then type in the argument, which is 100. Not 1,000. Almost. And then you're going to hit enter. You get 2. But here's the thing. You are not going to get your calculator for very many log. And this question, this one. So this question was on our provincial exam in January. It's the same thing as about setting it up as ratio. Love it. You're cool never knowing how to do it? Oh, I think you just jinxed everything. Yeah, no, we're good. I don't think there's a real witness. Okay, so Richter scale magnitudes, the shaky of the earth is measured on a scale. Okay. A initial is the amplitude for a standard earthquake. Okay, so they have an initial value. They're not telling you what it is. They're just saying A0, A to the or A subscript 0 is the shaky measurement of a standard earthquake. They're not telling you what it is. Shaky. Technical term. So in 1946, an earthquake struck Vancouver Island. It had an amplitude that was 10 to the exponent 7.3 times the regular shaky magnitude. Okay? Regular shaky. So what was the earthquake's magnitude on the Richter scale? So the Richter magnitude is this. Are you guys ready? You just stuck on the shaky? So A is going to be replaced with what? So A is equal to 10 to the exponent 7.3. Anything else in there? Times A initial. You guys with me so far? Because it is times A initial. This isn't the magnitude. It's 10 to the exponent 7.3 times what the regular magnitude is of an earthquake. So this one seems like it would be much more. So now what we're going to do is we're going to substitute all that information into the formula. So m is equal to log. What's the base on the log? 10 because it's not stated. So if it's not stated, it's 10. We said that the a we're going to replace with this. So this is going to be 10 to the exponent 7.3 times by A initial over A initial. That second A initial comes from the equation. So what happens to those A initials? So this is going to be magnitude of the log 10 to the exponent 7.3. Holy Hannah, we have exponents inside logarithms. Does anybody feel uncomfortable about that?
Yes.
Okay, so we're doing a little bit of laws before we start. So in this case, if your argument has an exponent on it, what happens to that exponent is it moves to the front. Yeah, remember? So m is equal to 7.3 log argument 10. There's something else you can do here. We talked about it already. What's the base on the log? What's the argument? So in the base of the argument, what's the value of that? 1. So what's the magnitude? There's no units of measure on the Richter scale. Does that make sense? Okay, let's good with that. Okay. Would you have picked that out? Impressive. I probably screwed up. All right. So now, some stronger recorded earthquake in Canada, struck somewhere where I've never been, had a Richter reading of 8.1. How many times as great as A initial was the amplitude? All right. Got it? Well, I know that goes in for the magnitude on the Richter scale, 8.1. And then we've got log A over A initial. What's the base on the log? Base 10. I'm going to change this into exponential form. So this would be 10 to the exponent 8.1 equals A over A initial. Am I done? What do I do, Jerome? A initial by both sides, yeah. Because I'm trying to solve for what A is. So A is equal to 10 to the exponent 8.1 times by the initial shaky measurement. You're right, this wasn't the question. It's coming up, the decimal question you remember. Sometime. Sorry, I could probably go through the notes and figure it out. Oh, no, it is. It's the compare. This is it. So this question was on the exam. Okay, I'm not losing that. Okay, so it says compare the shakiness of the 1949 earthquake with the earthquake from 1946. So what's the A value of the 46 earthquake? Not 1. So when you're comparing them, you got Vancouver. So which one goes on top? first one or the second one? How come? Nope. That's what they told us to do first. So they said compare this one to this one. So what's going to go on top? This A value. So this is going to be 10 to the exponent 8.1 times by A initial over, when you're comparing them, you're going to put them in a ratio, which really just means a fraction. And that's going to be 10 to the exponent 7.3 times by A initial. But it wasn't hard, but it looked terrible. Yeah, it looked terrible. But if you remembered how to do this, it would have at least given you some guidance. But how many people really remember this? Both Thompson and I looked at it, and I'm like, oh, I'm struggling on my nose. And you're like, I know, I it's good. Is it? Okay, so that's what we're doing in cheat sheets. Okay, so now we've got 10 to the exponent 8.1 over 10 to the exponent 7.3. Let's pull out some grade 9 math skills. What do we do? We have the same base, so we keep the base. What do we do with the exponents? Subtract them, so what are you going to be? 0.0. You didn't know that. Who taught you? Really? Who's inside? So what does that 6.31 mean? What does it mean? It is the answer. So what do we know? The 1949 earthquake was do that in your calculator. These would have been like these would have been. This you would have left if it was no calculator, you wouldn't have put 6.3. You would have left it as the exponent 0. So the 1949 quake was 6.3 times greater. Oh, there's supposed to be an E in there. Greater than the 1946 quake. Okay, okay. We are done. So, can you help me? Not listening.